M.W. Penn here to give you a quick review on adding fractions with unlike denominators. This is the easiest way to do it. We know that a fraction is written in two parts. The bottom number, or the denominator, tells us the number of equal parts dividing a whole, or dividing a unit. The numerator, the number on top, tells us how many of these equal parts we have. Let's look at these fractions. Here we have a unit divided into 2 equal parts, or halves, 3 equal parts, or thirds, and 4 equal parts, or fourths. We can have 1 of 2 equal parts, or 1/2, or 2 of 2 equal parts, 2 halves. But the denominator tells us how many equal parts are in the unit. And the top number is a very simple guy. He just tells us how many of these equal parts we have. We can easily add and subtract fractions that have the same denominator, because fractions that share the same denominator tell us that the units are divided into the same equal parts. And Bear would just say that that's a matter of counting up how many of the parts we have. Let's look at these fractions: 2/3 plus 5/3. Bear would just count up the number of thirds he has. Adding the numerators, we find that 2/3 plus 5/3 equals 7/3. Suppose we have units that are divided into 5 equal parts, or fifths. Again, to add them, Bear would say if we had 4/5 and then had 2/5 more, we would have 6/5, 6 of these 5 equal parts. If we had units divided into 4 equal parts, and we had 3 of them, 3/4, and then subtracted 2 of them, we would be left with 1/4. Just a matter of adding the numerators, or counting up how many we have. But what if we're trying to add parts of a unit that are not equal? That is, that we are trying to add fractional parts of a unit that do not have the same denominator. In this slide, we're attempting to add 1/3 of a unit to 1/2 of the same unit. We're looking at the problem in an area model and on the number line. When we perform this addition on the number line, we simply join together 2 segments, one the length of 1/3 of the unit, and one the length of 1/2 of the unit. When we join the segments together, we find that our answer is 5/6. So 1/3 of a unit plus 1/2 of the same unit is equal to 5/6 of the unit. 1/3 plus 1/2 equals 5/6. What if instead of adding thirds and halves, we were able to add sixths? Is there a way we can do that? We know that every space on the number line represents a particular quantity, so that if 2 numbers occupy the same space on the number line, they name the same quantity. So let's look at these numbers on the number line. Let's look at 1/2 and 1/3. What do we notice that's very interesting? 1/3 occupies the same space as 2/6, and 1/2 is at the same space as 3/6. So 1/3 is equal to 2/6, and 1/2 is equal to 3/6. Well, goodness, Bear can add sixths. He just finds out how many sixths he has. If he were to add 2/6 and 3/6, he would find that he had 5/6. It would be a very easy problem. But let's look at something else on this number line. Let's look at the unit 1. What do we see marking that unit? 1, of course, but also 2 halves and 3/3 and 6/6. They all name the same quantity. They all are equal to 1. Because a unit can be divided into equal parts in many, many different ways, we can have many different fractions that represent the same part of a whole. Here we're looking at a unit divided into 2 equal parts, 4 equal parts, 6 equal parts, and 8 equal parts. But the interesting thing here is that the numerator and the denominator are the same. So that when we have divided the unit into 2 equal parts, the numerator says that we have both of them. We have 2 halves. And when the unit is divided into 4 equal parts, we have 4 of them. We have 4/4. The same with 6/6 and 8/8. The interesting thing to note is that when a unit is divided into a certain number of equal parts, and the numerator tells us that we have all of those equal parts, we have the entire unit, or we have 1. 2 halves is equal to 1, 4/4 is equal to 1, 10/10, 20/20, they're all equal to 1. And 1 is the multiplicative identity. Do you remember what the multiplicative identity tells us? It tells us that any number multiplied by 1 is equal to that number. Multiplying by 1 does not change the quantity that a number represents. 4 times 1 is 4, 5 times 1 is 5, 10 times 1 is 10, and 1,000 times 1 is 1,000. So this is very important. Multiplying by the number 1 does not change a number. Now that we know that 1 is the multiplicative identity, and that any fraction that has the same numerator and the same denominator is equivalent to 1, we realize that we can multiply a fraction by n over n, or 1 in this form, and not change the quantity that the fraction represents. Let's multiply 1/3 by 1 in the form of 2 over 2. We see that the answer is 2/6. But 2/6 occupies the same space on the number line as 1/3. They're equivalent fractions that name the same quantity. If we were to multiply 1/3 by 3/3, the answer would be 3/9. But we see that 3/9 is an equivalent fraction to 1/3. They're at the same place on the number line. The same with 1/3 times 4/4, 4/12, or 1/3 times 5/5, 5/15. What we're saying is that if we divide a unit into 3 equal parts and we have 1 of them, or if we divide the unit into 6 equal parts and we have 2 of them, or if we divide the unit into 12 equal parts and we have 4 of them, 4 of 12 equal parts is the same as 2 of 6 equal parts is the same as 1 of 3 equal parts. They're equivalent fractions, and they name the same quantity. They are the same number. Well, now that we know that n over n equals 1, and we're trying to find equivalent fractions that have the same denominator so that Bear can add them up, let's look at this problem in a different light. Here, we're trying to add 1/2 and 1/5. But what if we were to find equivalent fractions for 1/2 and 1/5 that shared the same denominator? Well, if we multiplied 1/2 by 1 in the form of 5/5, the answer would be 5/10, and we know that it would be an equivalent fraction for 1/2. Suppose we were to multiply 1/5 by 1 in the form of 2/2. Well, goodness, our answer would be 2/10. And 2/10 is an equivalent fraction for 1/5. We don't really even have to add 5/10 to 2/10. We can let Bear do that. He would just count them up and find that he had 7/10. Let's try adding the simple problem of 1/4 and 2/3. When we're adding fourths and thirds, we know that we must find a common denominator for these fractions and then substitute equivalent fractions that share this denominator. If we were to multiply 2/3 by 1 in the form of 4 over 4 or 4/4, the product would be 8/12. That is a fraction equivalent to 2/3, but with the denominator of 12. Suppose we were to multiply 1/4 by 1 in the form of 3/3. Again, it would yield an equivalent fraction to 1/4, but the equivalent fraction is 3/12, and it also has a denominator of 12. Now the addition problem is just a simple one of counting up how many 12ths we have. 3/12 plus 8/12 equals 11/12. A problem suitable for Square Bear. So to add two fractions that have different denominators, the operation is really very simple. We convert each of the fractions into an equivalent fraction, and we make sure that these equivalent fractions share the same denominator. And the simplest way to do that is to multiply each of the fractions with 1 in the form of n over n, where n is the denominator of the other fraction. Not only is it very easy, it works. Let's add 3/5 and 2/6. Following our rule, we'll multiply 3/5 by 1 in the form of 6 over 6. And we find that the product is 18/30. Then we'll multiply 2/6 by 1 in the form of 5/5. The answer is 10/30. And then we simply let Bear add 18/30 to 10/30. He'll count them all up and find out that he has 28/30. So to add two fractions that do not share the same denominator, we simply have to follow a rule that's not hard to remember at all. We multiply each of the fractions by 1 in the form of n over n, where n is the denominator of the other fraction. To add 1/3 and 1/5, we would multiply 1/3 by 1 in the form of 5/5, and we would multiply 1/5 by 1 in the form of 3/3. We would find equivalent fractions for both 1/3 and 1/5, but these equivalent fractions would share the denominator of 15, and then we let Square Bear count up how many 15ths he has. 5/15 plus 3/15 equals 8/15. To add 1/3 and 3/4, we'd multiply 1/3 by 1 in the form of 4/4, and then we would multiply 3/4 by 1 in the form of 3/3. This would yield equivalent fractions with the common denominator of 12. Then we would let Bear add up 4/12 and 9/12, and he would find that the sum is 13/12. It's just a matter of finding out how many 12ths we have. 3/7 plus 1/2 means that we multiply 3/7 by 2/2, and we multiply 1/2 by 7/7. The equivalent fractions for both of those fractions are 6/14 and 7/14, and we'll let Square Bear add up 14ths. These are a few simple additions and one subtraction that I thought you might like to practice yourself. If you decide to do them, the answers are on my website, and the link to that page on the website is right here at the bottom of this slide. If you would like to further explore the Common Core State Standard algorithm for adding and subtracting fractions with unlike denominators, I do have a YouTube video that does this. The link is at the bottom of this slide. And I also have to say that the slides of this presentation are courtesy of MathWord Press.